In the preceding segment of our video series, we delved into the mesmerizing genesis of stars and binary star systems. If you're eager to catch up on the latest installment, I've conveniently pinned the link to the previous video in the comments section. Now, let's embark on our thrilling journey through the mysterious entities connected to stars, which, though different, influence the very fabric of the cosmos and determine its rules. Alright folks, let's press on with our exploration of white dwarfs. When it comes to our galaxy, these cosmic leftovers take the crown, outnumbering every single star out there. They're the leftovers of low-mass stars that have burned through their nuclear fuel and gracefully bowed out. Once formed, white dwarfs stick around for the long haul, cooling down over time thanks to the pressure exerted by their electrons. Most of them are here to stay, but there are always a few rebels that either explode or collapse under the influence of a nearby companion. Think about this. There could be anywhere from 10 billion to possibly 100 billion white dwarfs roaming around in our galaxy. And here's the kicker. We're still scratching our heads trying to figure out why some are heavier or lighter than others. So, the next time you are stargazing, spare a moment for these cosmic relics, reminding us of the incredible journey of stars and the mysteries that lie beyond. White dwarfs have been a treasure trove of insights into the evolutionary paths of their parent stars. However, astronomers faced numerous hurdles when attempting to study these mysterious objects, one being the vast distances separating us from them. Take, for instance, the nearest white dwarf, situated approximately 8.6 light-years away, which posed a significant challenge in data collection. To surmount this obstacle, astronomers devised a clever method leveraging principles of seismology to unveil the inner workings of white dwarfs. Similar to how earthquakes help geologists explore the Earth's depths, these stellar remnants naturally exhibited oscillations in response to internal radiation flow, resulting in subtle variations in brightness. Conducting seismology on white dwarfs required painstaking observations spanning days to weeks. However, the interruption caused by sunrise each day complicated continuous monitoring. In response, astronomers introduced the ingenious whole Earth telescope technique. This strategy coordinated a global network of small telescopes via telephone and the World Wide Web. By strategically scheduling observations to align with sunrise and sunset across different regions, astronomers were able to achieve uninterrupted monitoring of target white dwarfs for extended periods. The results have been nothing short of extraordinary. By harnessing the power of the whole Earth telescope, astronomers have achieved precise measurements of certain white dwarfs' masses. They've also scrutinized the rotational characteristics of select stars and delved into the inner compositions rich in carbon and oxygen. The outer hydrogen and helium shells have provided crucial insights into the birth of these white dwarfs. These methods, among others, have made it possible to estimate the ages of specific white dwarfs. Unraveling the ages of white dwarfs holds a special allure as it unveils the saga of our galaxy's past. Since nearly all white dwarfs ever formed are still in existence, they serve as witnesses to the early epochs when our galaxy was in its infancy. While white dwarfs cool down gradually over time, their cooling process is slow. The oldest and coldest white dwarfs, though challenging to spark, yield invaluable information. Studies on these ancient white dwarfs suggest that the earliest ones emerged approximately 10 billion years ago, indicating that our galaxy took shape only a few billion years prior. This deduction implies that our galaxy's age is relatively young compared to certain estimates. Though the exact age of our galaxy remains uncertain, estimating it through white dwarfs has become a reliable method. Many white dwarfs in our galaxy aren't alone, but are in pairs. These binary white dwarfs are interesting because they're like more exotic objects such as neutron stars and black holes in binary systems. Most of them form when the most massive star in the pair becomes a white dwarf and passes some of its mass to its partner. Sometimes both stars give away mass, creating two white dwarfs in orbit. In some cases, the next phase of mass transfer leads to cataclysmic variables. This is an important phase of white dwarfs. Before delving into this topic, I kindly ask you to subscribe to my channel. Subscribing is free for you, but greatly supports us in creating more content like this. Basically, cataclysmic variables are binary systems where one star gives its mass to the other, forming a disk around the white dwarf. The key parts are a star losing mass, often smaller than its white dwarf companion, and the material stream merging with the disk. The main source of light in these systems isn't the white dwarf or the losing star, but the hot spot where the stream collides with the disk's edge, generating heat and light. Some light also comes from friction and heating within the disk. Various categories of cataclysmic variables exist, each distinguished by their unique observational characteristics and the underlying mechanisms believed to drive their variability. Cataclysmic variables are a type of nova or new star, but they aren't truly new stars. Instead, they become visible during intense flares. The term supernova evolved from this idea, referring to even brighter flaring events, often in distant galaxies. While novae and supernovae are different phenomena, they're related. Some novae may evolve into supernovae, and certain novae involve thermonuclear explosions. Dwarf novae represent the mildest form of cataclysmic variables. They exhibit irregular flare-ups, becoming approximately 10 times brighter than their usual luminosity. These flares occur intermittently over periods ranging from weeks to months and persist for days to weeks at a stretch. The duration of these flares is too brief to accumulate a significant reservoir of thermonuclear fuel. Instead, the energy involved originates from the heating as material from the mass-losing star settles within the gravitational field of the white dwarf. Two competing theories explain the mechanism behind these flares. One hypothesis suggests that the mass-losing star experiences surges, intermittently ejecting additional mass. However, this explanation faces a challenge, as one would anticipate the hot spot to flare first, preceding the disk, which contradicts observations. An alternative theory proposes that matter accumulates in the accretion disk until an instability triggers a sudden inward spiral towards the white dwarf. This process leads to an escalation in frictional heating and light output. In-depth studies show that dwarf novae are mainly triggered by a disk heating instability. Matter builds up in the disk during a cool phase until it becomes opaque, trapping heat. This causes more heating, friction, and opacity, creating a loop that rapidly heats up the disk, leading to a dwarf nova outburst when the central star is a white dwarf. These outbursts can also heat up the companion star's surface, possibly causing more mass transfer. Both of these mechanisms likely play a role in causing dwarf nova outbursts. Classical novae produce significant explosions, but their power is vastly lower compared to supernovae. Recurrent novae, on the other hand, experience flares that elevate their brightness to about 1,000 times that of pre-outburst conditions. These flares occur at intervals ranging from 10 to 100 years, yet the mechanism behind these outbursts remains unknown. While both systems involve mass transfer through an accretion disk onto a white dwarf, the occurrence of dwarf novae outbursts or recurrent nova outbursts is exclusive to each system. This discrepancy may stem from differences in the rate of mass transfer. If the transfer rate is sufficiently rapid, the disk channels all mass steadily to the white dwarf. without accumulating enough matter to initiate dwarf nova outbursts. However, this explanation does not elucidate the nature of recurrent nova outbursts. Classical novae, also known simply as novae, ignite the night sky by amplifying their brightness dramatically, from 10,000 to 100,000 times their normal state. Intriguingly, such spectacular flares have never been observed to repeat. There exists a long-standing suspicion among astronomers that classical novae may recur every 10,000 years, yet direct evidence remains thin, extending well beyond the concise history of astronomical records. The underlying mechanics of these brilliant phenomena are supported both by observational insights and theoretical models, pointing towards thermonuclear explosions. The process starts by pulling material from a nearby star onto the white dwarf. This material piles up densely on the white dwarf's surface, kept in place by something called quantum pressure. This outer layer is rich in hydrogen, which, unlike the carbon and oxygen-rich core of the white dwarf, ignites quite effortlessly under increasing pressure and temperature. Since hydrogen readily catches fire, the quantum pressure in this phase crucially keeps the thermonuclear burn steady and contained, preventing early expansion and cooling, which would otherwise quench the reaction. This meticulous balance allows for an explosive burst, predominantly affecting the outer layers of the star, contrasting starkly with the all-encompassing disruption seen in supernovae. This phenomenon culminates in an explosive display, casting off intense light and ejecting stellar material at incredible velocities. The cycle is poised to repeat, with the white dwarf continuously accruing hydrogen from its companion, setting the stage for yet another cosmic spectacle. In most cataclysmic variable stars, the star losing mass is usually a small main sequence star. Let's consider a scenario. If a small main sequence star sheds mass, it must be in its Roche lobe. Since the star is small, its Roche lobe is also tiny, meaning the main sequence star and the white dwarf are very close, possibly even touching. This raises an odd question. How did the white dwarf form in such a close distance to the main sequence star? To understand why the stars are close now, we need to consider how far apart they were initially. If the white dwarf's parent star had enough space to become a red giant before material started flowing onto it, they must have been far apart. This means they couldn't have formed a cataclysmic variable system. So, even though they're close now, they started far apart. To do this cool space move, we need to bring the stars closer to each other. We plan to do this using something called a common envelope. Here's how it works. When a big, old star, called a red giant, starts giving away its stuff to its smaller companion star, it does so really fast. Sometimes, it gives away so much stuff that the other star can't handle it. All this stuff creates heat and light, and the pressure from all that heat and light makes it hard for more stuff to go onto the second star. So, instead of just swirling around the stars in a flat circle like a pancake, all this stuff forms a big bubble around both stars, kind of like a giant balloon. Inside this bubble, the original red giant's core and the other star orbit each other. This setup is called a common envelope. Now, instead of floating around in space, the stars are moving through this gas bubble. The friction from all that gas makes the stars slowly come closer together, like they're spiraling in. As the story goes on, the small white dwarf and the main sequence star get closer and closer until they're really near each other. The main sequence star gets so close that its gravity bubble, called the Roche lobe, becomes smaller than the star itself. It's interesting that the star doesn't change its size to fit the bubble. Instead, the bubble shrinks to fit the star. At this point, maybe because of all the excited talk among scientists, a burst of energy pushes out the big gas bubble they were both in. As the gas flies away, it leaves behind a new kind of star system called a cataclysmic variable. In this situation, the star system starts inside the big gas bubble, with the main sequence star already giving stuff to the white dwarf. When the main sequence star starts giving away stuff to the white dwarf, it might trigger the burst of energy that kicks out the gas bubble. The most straightforward, yet less common, mass transfer scenario involves the red giant envelope flowing from one star to the other, thus exposing the white dwarf core. Subsequently, the second star expands to fill its Roche lobe and transfers mass back to the white dwarf, resulting in the formation of a cataclysmic variable. While this simplistic depiction may occur infrequently, the formation of most cataclysmic variables likely entails the more intricate common envelope process, despite many remaining details yet to be elucidated. As time elapses, the predetermined fate of these variables unfolds. The destiny of cataclysmic variables remains highly uncertain, with two potential outcomes looming. Firstly, these systems could simply fade away. In such a scenario, the ordinary star might shed its envelope, leaving behind a second white dwarf and halting the process of mass transfer. Alternatively, cataclysmic variables might culminate in a dramatic implosion or explosion. Even the gradual decline holds intrigue, promising intriguing twists and turns. Let's delve into the catastrophic scenarios first, before revisiting the possibility of a gradual fade-out. In some cataclysmic variables, certain white dwarfs hover around 10% below the Chandrasekhar limit, sparking curiosity about what happens if they exceed this threshold. One outcome could be the ignition of nuclear fuel within the dwarf, comprised mainly of carbon and oxygen. As it nears the limit, the dwarf becomes extremely dense, enabling carbon burning even without substantial heat. Though this process is highly unstable and could trigger a massive explosion. This explosion would occur in a star depleted of hydrogen, possibly retaining a small amount on its surface. Alternatively, the white dwarf might consist of elements like iron, which disintegrates under compression, or oxygen, neon, and magnesium, which absorb electrons rapidly. Approaching the Chandrasekhar limit in such cases could lead to collapse rather than explosion, resulting in the formation of a neutron star orbiting a main sequence star, with minimal to no mass ejection. The collapse would primarily emit neutrinos, possibly with limited optical display but significant brightness. The occurrence of these potential catastrophes hinges on the mass nearing the critical value of the Chandrasekhar mass, within a narrow margin, but an intriguing question remains unanswered: whether the mass ever reaches such high levels. Nova explosions usually blow away built-up material from the surface of a white dwarf. If everything on the surface is blasted away, the white dwarf's mass stays the same. Also, these explosions often throw out extra carbon and other heavy stuff, hinting they might push out material from inside the white dwarf too. This could mean the white dwarf's mass decreases because of nova explosions. If this is true, the white dwarf sticks around in the binary system until its partner star transforms into its own white dwarf. So, nova explosions could set up situations where the cataclysmic variable slowly fades away instead of going through a big disaster. The cataclysmic variable may eventually diminish in activity, but the narrative doesn't conclude simply because the system yields two white dwarfs. The inquiry now shifts towards the ultimate destiny of these orbiting white dwarfs. Devoid of the capacity for independent evolution, they would gradually cool off if left undisturbed, supported solely by quantum pressure. However, their tranquility is short-lived. Their orbital movement generates gravitational waves, siphoning off energy and angular momentum, consequently causing their orbit to contract. As discussed previously, Gravitational radiation influences all stellar orbits, albeit to a minor extent compared to other interactions between stars. Only when the two white dwarfs reach a state of complete calmness does the subtle impact of gravitational radiation become significant. This inevitability leads to the spiraling together of the two white dwarfs, with the outcome dictated by their unique properties as stars sustained by quantum pressure. In the case of a typical star upheld by thermal pressure, an increase in mass results in an expansion of the star's radius, while a reduction in mass causes contraction. Conversely, for a white dwarf supported by quantum pressure, the opposite holds true. Additional mass leads to an overall compression of the star, resulting in a decrease in radius, whereas mass removal allows the star to expand in the reduced gravitational field, thereby attaining a larger radius. This behavior holds critical implications for the eventual fate of one of the white dwarfs. In the end, the destiny of a white dwarf or a neutron star hangs in the balance, swayed by the weight they bear or the company they keep. Will they endure throughout eternity, fading into obscurity as black dwarfs, or will they plunge into the cataclysmic abyss, unleashing the most colossal disaster the universe has ever witnessed, the supernova? Time has all the answers, but for now, let us venture into the supernova, the bigger event than this variable. Which stars meet their explosive demise? Which succumb to the relentless grasp of gravity, collapsing into oblivion? And which defy the cosmic odds, settling into a serene existence as white dwarfs? Astrophysicists are piecing together the answers to these profound questions, unraveling the mysteries of stellar fate. We've learned that tranquility is not granted to all stars. Some meet their end in a blaze of glory, exploding into supernovae, a dazzling spectacle where a single star outshines entire galaxies. Estimates of the colossal energy involved suggest that these cosmic eruptions obliterate a significant portion, if not the entirety, of the star itself. Throughout history, careful observations, particularly those meticulously documented by the Chinese, reveal the occurrence of 7 or 8 supernovae within our corner of the galaxy over the past 2 millennia. The supernova of 1006, dubbed the brightest ever recorded, illuminated the night sky with such intensity that one could read by its radiance. Across the Middle and Far East, astronomers marveled at this celestial event. Yet, it is the supernova of 1054 that reigns supreme in the annals of astronomical lore. Though it stands as the most renowned, it is not the sole phenomenon of its kind documented as a Chinese guest star. This spectacular explosion birthed the expansive shell of gas now known as the Crab Nebula, first observed by the Japanese and prominently noted by the Koreans, while the Chinese meticulously preserved records of its occurrence. Speculation even suggests that Native Americans may have depicted this cosmic event in rock art and pottery, though definitive evidence remains elusive. It's quite puzzling why European history remains silent about the supernova event. Some suggest that during the Middle Ages, the Church's influence was so profound that any deviation from the belief in the unchanging heavens was stifled. However, an intriguing theory proposes that medieval European monks, known for their unmonastic behavior, might have recorded such celestial phenomena despite their vows of abstinence. Nonetheless, the absence of records could simply be due to obstructed views caused by weather or terrain. In contrast, Europeans didn't miss the chance to document supernovae centuries later. In 1572, Tycho Brahe, a prominent astronomer, meticulously observed a supernova, providing valuable data on its brightness evolution. His work paved the way for Johannes Kepler's groundbreaking laws of planetary motion. Kepler himself witnessed a supernova in 1604, confirming Tycho's findings. These supernovae are believed to be type first-A events, according to modern astronomers. Following Kepler, Galileo and Newton revolutionized astronomy with telescopes and new laws of mechanics. Despite advancements, observing supernovae remains challenging due to their infrequent and unpredictable nature. However, the remnants of exploded stars, like Cassiopeia A, offer valuable insights. Although Cassiopeia A's underwhelming optical brightness in 1667 contrasts with typical supernovae, it still fascinates astrophysicists studying these enigmatic cosmic events. In July 1999, the Chandra Observatory was launched, finally uncovering the elusive compact object within the massive star's remnant, a quest that spanned decades. Surprisingly, the very first image captured by Chandra revealed a faint dot of X-ray emission at the center of the supernova cloud, previously unseen due to its low luminosity. This mysterious object raises questions. Is it a neutron star, or a black hole accreting matter from its surroundings? Despite an amusing poll on the Chandra website, science demands evidence beyond speculation. Regular pulses of emission, typical of rotating neutron stars, have not been detected yet. A notable pattern emerges from historical supernovae and their remnants. Some leave behind compact objects, while others don't. This distinction hints at two fundamental explosion mechanisms. One involving the core collapse of a massive star, leaving behind a compact remnant, and the other obliterating the star entirely. The presence of elongated structures or jet-like flows often accompanies the observation of compact remnants, as seen in the Crab and Cassiopeia A remnants, among others. Conversely, supernovae lacking compact remnants typically exhibit no significant elongation, as seen in events like 1006 supernova and Tycho's supernova. Supernovae directly observed since 1604, except for Cassiopeia A, have occurred in distant galaxies. While such events are rare within a single galaxy, the vast number of galaxies observed by astronomers increases the chances of detecting supernovae. Following supernova 1987A, the rate of discovery rose to about 100 per year, although many are distant and faint, yielding limited data. Nonetheless, specialized programs have provided valuable insights into very distant supernovae. Astronomers have categorized supernovae in distant galaxies into two main types known as type first and type second. This classification originated in the 1930s through systematic searches conducted by Fritz Zwicky at Caltech. Traditionally, supernovae types are distinguished by their spectra, revealing the composition of the ejected material. Additional insights come from analyzing the light curve, which depicts the rapid brightening followed by slower dimming characteristic of each event. However, as more supernovae are discovered, some events exhibit properties that blur the lines between type first and type second. Like any evolving field of science, the goal is to move beyond simple categorization and develop a deeper physical understanding of these phenomena. The spectra of type first supernovae are distinct because they lack detectable hydrogen, which is abundant in the universe. Type I supernovae, particularly type first A, occur across various galaxy types, including elliptical, spiral, and irregular. However, they tend to avoid the spiral galaxy arms, where new star formation occurs. This suggests that type first A supernovae originate from older, longer-lived stars, indicating they are not highly massive, as massive stars have shorter lifespans. The mass range of type first A progenitor stars is currently a subject of debate. The light curve of type first A supernovae is characteristic, with an initial rise to peak brightness over approximately 2 weeks, followed by a gradual decay over months, consistent across all events. Historical records from Tycho and Kepler indicate they observed type first-A supernovae, although no other galactic supernova records are extensive enough for type identification. Recent observations have revealed slight variations among type first-A supernovae, challenging previous notions of uniformity. In contrast, type second supernovae exhibit normal abundances of hydrogen in their ejected material, resembling the outer layers of the Sun near peak brightness. These supernovae are absent in elliptical galaxies and primarily occur in spiral galaxies, particularly within the spiral arms. This suggests that Type II supernova progenitor stars are born and remain within the spiral arms due to their short lifespans, indicating their high mass. The light curve of a typical Type II supernova shows a rapid rise to peak brightness in 1 to 2 weeks, followed by a nearly constant light output for a month or two before a sudden drop, followed by a slower decline over months. This pattern aligns with an explosion occurring in the core of a star with a massive, extended red giant envelope. Adding to the complexity, in the 1980s, astronomers identified 1, and possibly 2, additional types of hydrogen-deficient supernovae, Type 1b and Type 1c. These types are likely closely related, unlike Type 1a, but similar to Type 2. Types 1b and 1c typically occur in the arms of spiral galaxies, indicating their association with massive stars. Type 1b supernovae exhibit signs of helium in their spectrum near peak brightness, while Type 1c supernovae show minimal or no evidence of helium. However, both types show evidence of oxygen, magnesium, and calcium at later stages, suggesting their close relation. Unlike Type 1a supernovae, which predominantly exhibit iron in their spectra at later stages, Types 1b and 1c suggest a composition similar to that expected in the core of a massive star depleted of hydrogen, with Type 1c potentially lacking helium as well. This implies a possible origin in stars resembling Wolf-Rayet stars, although a direct connection has yet to be confirmed. The light curves of Types 1b and 1c resemble those of Type 1a, but are dimmer at peak brightness. In 1993, the observation of the bright supernova SN 1993J provided further insights into the diversity of processes leading to stellar explosions. Initially categorized as a Type II, Supernova 1993J displayed hydrogen in its spectrum, indicating a Type II-like event. However, as the explosion progressed, the hydrogen features diminished, and evidence of helium emerged, resembling a Type 1b. Similar transitional events have been observed before and since. It appears that the supernova likely had most, but not all, of its hydrogen envelope removed, possibly through a binary mass transfer process. In other cases, hydrogen removal may be more complete, and for Type 1c, helium removal may also occur. While direct observational evidence for binary companions in Types 1b or 1c, or transition events like Supernova 1993J, is lacking, computer models suggest this possibility. At least for the supernova, the role of strong winds from massive stars versus binary mass transfer in Types 1b or 1c remains unresolved. The available evidence suggests that Types 2nd and 1st, B or C supernovae result from the explosion of massive stars. These stars are believed to have progressed from the main sequence to red giants, undergoing various stages of nuclear burning that produce increasingly heavier elements in their cores. However, the specific types of massive stars involved in this process remain a subject of debate. One method of inferring the masses of stars that undergo supernova events is by analyzing the frequency of these events in different galaxies and comparing them to the rate of star formation across a range of masses. In galaxies like ours, numerous low-mass stars are born annually, while massive stars are relatively scarce. However, Stars with masses exceeding about 20 solar masses are born and die too infrequently to account for the rate of type-second supernova explosions. Conversely, stars with less than about 8 solar masses die too frequently. Stars with masses between approximately 8 and 20 solar masses, which die at a rate of about once per 100 years in our galaxy, align with the estimated occurrence rate of type-second supernovae. It is likely that type-second supernovae originate from stars within this mass range. Many of these stars, particularly those at the upper end of the mass spectrum, are believed to develop iron cores that collapse, leading to the formation of neutron stars. There is thus a strong indication that type-second supernovae result in neutron stars as compact remnants of the explosion, with the gravitational energy released during the formation of the neutron star driving the explosion itself. The driving force behind the explosion of types first B and first C supernovae remains uncertain due to the limited number of observed events. However, their occurrence rate appears to be similar to that of type-second supernovae, suggesting they may originate from a comparable mass range. One hypothesis proposes that types first B and first C stem from Wolf-Rayet stars formed via intense stellar winds in stars exceeding 30 solar masses. However, this alone may not account for their frequency, indicating potential origins from stars with less than 30 solar masses, possibly requiring a binary companion to strip away the hydrogen envelope. Despite these uncertainties, the core collapse mechanism associated with type-second supernovae likely applies to types first B and first C, suggesting their association with the formation of neutron stars. For stars with masses between approximately 8 and 12 solar masses, a slightly different evolutionary path may occur. While the ultimate outcome of core collapse remains the same, computer simulations indicate that when carbon burning occurs, the core remains supported by thermal pressure. As the core contracts, quantum pressure becomes significant before other fuels can ignite. This leads to the formation of cores composed of oxygen, neon, and magnesium, with the collapse triggered by electron absorption, converting remaining nuclear fuels into iron. This process may result in the production of rare heavy elements like platinum. To explore which stars avoid exploding and instead transition into white dwarfs, scientists analyze the number of white dwarfs in different stellar clusters and infer the types of stars that produce them. This analysis suggests that stars below approximately 8 solar masses typically evolve into white dwarfs without undergoing supernova explosions immediately. The rate of neutron star formation in the galaxy aligns closely with the rate of type-second supernova formation. While this correlation doesn't conclusively demonstrate that type-second supernovae always lead to neutron star formation, it's widely accepted as a working hypothesis. However, challenges arise in explaining how the energy released during neutron star formation could trigger a supernova explosion. Despite efforts, some computational models continue to predict total collapse rather than explosion. These discrepancies may stem from missing pieces of physics in the calculations, such as the effects of rotation or magnetic fields, or the inherent complexity of the process. It's also possible that not all collapsing cores result in explosions. Some may form black holes without any accompanying explosion. Stars with a starting mass over 20 times that of our Sun are expected to form iron cores that collapse. However, there aren't many of these stars, so whether they explode or not won't greatly affect the total supernova rate. We need other methods to determine if they explode. One clue suggesting some massive stars explode is that about 1% of star material is made of elements heavier than helium, which can't be created during the Big Bang. Heavy elements are naturally produced in massive stars, and if they explode, they scatter these elements into space, enriching it for new stars. Stars weighing between 8 and 15 solar masses likely don't contribute much to heavy element production because they lack them outside their collapsing cores. Stars between 15 and 100 solar masses, however, produce significant amounts of heavy elements. If they explode, the newly formed heavy elements mix with interstellar gas, aiding in the creation of new stars with proper heavy element content. Initially, it was widely believed that the most massive stars explode and create heavy elements, but more accurate observations hint at reassessment. Detailed spectra of stars reveal discrepancies in heavy element production, suggesting some massive stars might collapse entirely. This means some explode, ejecting heavy elements, while others leave behind black holes. The most plausible scenario might involve stars from 8 to 30 solar masses exploding, while those from 30 to 100 solar masses collapse, retaining their heavy elements. Ultimately, we still lack enough understanding of stellar processes to confidently determine which stars explode and scatter heavy elements. Let's delve into the mysterious process by which these stars explode, unleashing a cascade of events that ultimately return the very elements that compose us, our planet, and everything we behold. During the collapse of an iron core, protons capture electrons, transforming into neutrons and generating neutrinos in the process. This conversion of composition to neutrons is crucial for the formation of a neutron star. With each neutron formed, a corresponding neutrino is produced, resulting in a significant number of neutrinos being emitted. As the collapse progresses to the density of atomic nuclei, the strong nuclear force exhibits a repulsive aspect, creating an outward pressure. Additionally, the quantum pressure exerted by the neutrons becomes influential. These combined pressures cause the collapse to pause, at least temporarily. Dropping a heavy object like a bowling ball releases significant energy upon impact, with the energy proportional to the object's mass and the distance it falls. Consider dropping a bowling ball and then a sports utility vehicle from the top of a tall building to visualize the difference in energy release. Now, imagine the immense energy release when a star collapses from the mass of the Sun to the tiny size of a neutron star, mere kilometers across. This process generates a tremendous amount of energy, capable of blowing off outer layers containing various elements. However, a substantial portion of this energy is lost as neutrinos, which can easily escape from the newly formed neutron star along with the infalling matter. If only a fraction of the energy remains after neutrino loss, it can still trigger an explosion, but if too much is lost, the explosion fails, leading to the continued collapse of the neutron star into a black hole. Determining the exact percentage of energy lost to neutrinos, typically ranging from 99 to 99.9%, is crucial but immensely challenging due to uncertainties in the complex physics involved in core collapse. Moreover, the explosion process tends to be self-limiting. Trapping more energy slows the rate of infall, reducing the energy available to power the explosion. Despite decades of computer simulations, results remain inconclusive, with some predicting explosions and many resulting in complete collapse to form black holes. Astrophysicists continue to grapple with these complexities, striving to unravel the intricacies of stellar explosions, while acknowledging that stars themselves seem to effortlessly produce these phenomena. In recent decades, research into this subject has focused on two primary mechanisms for potentially reversing the collapse of an iron core to trigger a supernova explosion. One of these mechanisms is known as core bounce. When a neutron star is newly formed, it initially exceeds its equilibrium state, resulting in significant compression of the neutron core. This compression leads to a subsequent rebound, sending a powerful shock wave back through the collapsing material. The collapse of the core typically takes around 1 second after instability begins, while the core bounce generates the shock wave in approximately 0.01 seconds. If successful, this rapid process can generate a massive explosion. However, for the explosion to occur, the shock wave must possess sufficient strength to eject the outer layers of matter, leaving behind the neutron star. Yet, the shock wave encounters obstacles as it travels through the infalling material. Some of its energy is dissipated through the production and loss of neutrinos, and it must also break down the infalling iron into lighter elements to form the neutron star. Consequently, the shock wave can stall, lacking the energy to reach the star's outer layers. Material continues to fall onto the stalled shock front, akin to a bow wave encountering an obstacle in a stream. This stalled shock front accumulates matter, gradually crushing the neutron star into a black hole. Most current calculations indicate that the core bounce alone is insufficient to trigger a supernova explosion. The alternative mechanism under consideration capitalizes on the vast flux of neutrinos emanating from the neutron star. While regular matter, such as the Sun, is largely transparent to neutrinos due to their interaction solely via the weak nuclear force, neutron star matter, nearly as dense as an atomic nucleus, presents an exception. This dense matter can be either opaque or partially transparent to neutrinos. Although the majority of neutrinos escape into space, a fraction becomes ensnared in the hot material just beyond the shock wave initiated by the core bounce. The gradual accumulation of neutrino heat could potentially reignite the shock, propelling it outward and instigating the explosion. This process unfolds relatively slowly, over the course of about a second. The mechanism for trapping a portion of the neutrino energy behind the shock may be linked to the boiling phenomenon observed in newly formed neutron stars. Upon the cessation of collapse and the subsequent rebound of the neutron star, it attains extreme temperatures, leading to a boiling effect akin to water in a heated pan. This boiling facilitates the upward transport of heat, or in the case of neutron stars, the outward dispersal of neutrinos through mechanical motion. Under specific conditions, this boiling process may be substantially more efficient in neutrino transport compared to slower radiation leakage processes. However, accurately modeling this process within neutron stars poses significant computational challenges due to the intricate nature of motion. Nevertheless, contemporary simulations depicting motion in multiple dimensions consistently indicate the occurrence of boiling in neutron stars. It is widely agreed that explosions are improbable without this boiling phenomenon. Yet debates persist regarding its adequacy in triggering an explosion. For the past 30 years, most calculations regarding the collapse of the core and its aftermath have assumed a spherical shape. Even if the neutron star experiences boiling, it might still maintain an overall spherical symmetry in its structure. However, there are indications suggesting that the explosions resulting from core collapse are not perfectly spherical. Matter may be expelled more forcefully in certain directions compared to others. There have been hints of this idea for some time. For instance, when we observe neutron stars as rotating, magnetic pulsars, and examine the expanding gas clouds from supernova explosions, known as supernova remnants, we notice evidence of non-spherical behavior. The well-known Crab Nebula isn't circular. X-ray images from the Chandra Observatory reveal a torus of matter ejected by the neutron star, along with jets of fast-moving material shooting out in opposite directions along the axis of the torus. The neutron star itself is moving directly along one of these jets. Similarly, Cassiopeia displays signs of a jet-like flow in one direction and a somewhat less defined flow in the opposite direction. However, unlike the Crab pulsar and a few other cases, The compact object in Cassiopeia seems to be moving perpendicular to the orientation of the jets, rather than in line with them. This observation holds a clue, though its significance remains unclear. So, until recently, we knew that the remnants of core collapse often resulted in rotating, magnetic neutron stars. However, it wasn't clear whether rotation and magnetic fields were essential to the explosion process or merely incidental. Similar uncertainties surrounded the asymmetries observed in various supernova remnants. Were these features unique to a few supernovae, or did they hint at a broader pattern? Measuring the polarization of light emitted by supernovae has given scientists a fresh perspective and valuable insights into the explosion process. Electromagnetic radiation comprises an electric component oscillating perpendicular to a magnetic component, both perpendicular to the wave's direction, or photon, in quantum terms. When we measure light polarization, we're essentially determining the direction of the electric field's oscillation. In supernovae, light scatters off electrons in the outer material before reaching telescopes on Earth, millions of light years away. This scattering results in an average electric component orientation perpendicular to the supernova's surface. If the supernova is perfectly spherical, or appears so from our viewpoint, light will come from all directions equally, resulting in no net orientation of the electric component. However, if the supernova material is asymmetric, some parts will emit more light and more accurately represent their surface orientation than others. This leads to a net orientation of the electric component in the light received by astronomers, allowing them to measure polarization. In essence, if a supernova displays net polarization, it can't be perfectly spherical. Its shape might resemble a pancake or cigar, or something more complex, but it won't be round. Around a decade ago, astronomers began collecting polarization data on accessible supernovae. As astronomers began analyzing the data, they noticed a clear distinction between Type Ia supernovae and core collapse supernovae. Type Ia supernovae, both near and after peak brightness, showed little to no polarization, indicating they were essentially spherical. On the other hand, all core collapse supernovae exhibited significant polarization, indicating they were definitely not spherical in shape. As more data accumulated over the years, it became evident that the polarization strength increased as the supernova aged and thinned out, allowing astronomers to see deeper into its core. This suggested that the asymmetry wasn't just a surface feature, but extended to the inner depths, indicating that the explosion mechanism itself was asymmetric. Furthermore, Type Ia supernovae, which have shed their hydrogen and helium envelopes, also showed high polarization. This indicates that even at early stages, astronomers could peer deeper into the explosion, revealing its non-spherical nature driven by the explosion process. Another crucial observation was that the polarization wasn't random in many cases. The orientation of the electric field consistently pointed in the same direction, regardless of time or observed wavelength. This suggested that the ejected material from the supernova was propelled along a specific direction during the explosion. However, further analysis revealed that this behavior wasn't universal. Sometimes different elements ejected from the explosion indicated more than one direction, while in other cases, the data suggested truly random directions in space. Nonetheless, the tendency for ejected material to align in a particular direction remains a significant aspect in many cases, providing valuable insights into the underlying mechanisms of supernova explosions. In typical scenarios, if a supernova appears to be pointing in a particular direction in space, then one question arises: how could this happen at first place? The most straightforward explanation seems to be rotation. A stationary sphere lacks a preferred orientation. while a rotating one, such as a planet, star, or galaxy, aligns with its axis of rotation. Rotation naturally selects a specific direction, although which direction it is depends on chance factors during formation and subsequent movements. Nevertheless, it's an inherent characteristic of a rotating object. However, there are other ways to establish special directions that don't rely on rotation. For example, the newborn neutron star might oscillate relative to the surrounding stellar material, shifting back and forth between different directions. As we began to gather polarization data, our initial thought was about jets. Jets blowing along particular directions are common in systems where gravity pulls matter in, such as protostars and the centers of galaxies, or from black holes in binary star systems. The collapse of the iron core to form a neutron star is an extreme version of such a system. We speculated that similar processes might be at play in core collapse supernovae. Another crucial aspect is magnetic fields. As discussed earlier, pulsars are neutron stars that rotate and possess magnetic fields. Many theories regarding the formation of jets rely on the entanglement of magnetic fields. Therefore, it's conceivable that magnetic fields play a significant role in the supernova explosion process. Astronomers investigated the magneto-rotational instability, which amplifies magnetic fields in systems with shear, where matter moves past other matter. The collapse of the iron core naturally creates shear, much like a skater pulling in their arms, causing the neutron star to spin faster than the original core. This process drives the magneto-rotational instability, which rapidly enhances any weak magnetic fields present in the iron core. This suggests that magnetic fields will naturally strengthen in this environment. It's inadequate to consider only rotation without considering the magnetic field. They are interconnected in the core collapse setting. The critical question is the size of the magnetic field and its effect on matter. While challenging, the polarization data suggests that rotation and magnetic fields are intimately linked to the explosion process, shaping it if not directly causing it. The polarization indicates that rotation and magnetic fields likely play a crucial role in the actual explosion process of supernovae. If this is true, then current numerical calculations might be overlooking a significant factor necessary for causing an explosion. Rotation is the most apparent mechanism for disrupting spherical symmetry by defining a rotation axis. Properly accounting for rotation, aided by magnetic fields, may be essential for fully understanding when and how collapse leads to explosions. During collapse, all the energy is supplied by gravity, temporarily splitting into two parts: a hot bath of neutrinos that gradually leaks out of the neutron star, and the immense rotational energy of the neutron star itself. Utilizing this rotational energy and directing it along the rotation axis could be the key process that triggers and shapes core collapse supernovae explosions. Incorporating the effects of rotation and magnetic fields poses an even greater computational challenge, but as computing power continues to advance, progress in this area is expected in the coming years. To explore the role of jets in supernovae, astronomers investigated how jets might affect supernovae. While this calculation simplified some aspects that require further investigation, it addressed fundamental issues by assuming that a newly formed neutron star could produce jets along its rotation axis within about a second, while the outer parts of the star waited to be expelled into space or to collapse into a black hole, depending on the collapse outcome. By omitting the hydrogen envelope of a massive star model to correspond to type 1b or 1c supernovae, the calculation focused on the core of helium and heavier elements. The jets reached the surface of the helium core in approximately 6 seconds, generating bow shocks that spread sideways as well as forward, similar to a motorboat creating a bow wave on a lake. However, in a star, The bow waves spread outward like flower petals and wrap around the star. If the jets are symmetrical in the up and down directions, the converging bow shocks eject matter along the equator, resulting in a strongly asymmetric, donut-like explosion in the equatorial direction. While polarization observations cannot definitively prove this shape, the data are consistent with this explanation for the observed polarization in many cases. Another aspect to consider is the relationship between the final spin and magnetic field of the neutron star and the original spin of the iron core. If the iron core spins slowly, the resulting neutron star will also spin slowly and generate a weak magnetic field. Conversely, a faster spinning iron core leads to a faster spinning neutron star with a stronger magnetic field. However, if the iron core spins too rapidly, the centrifugal force will provide additional support to the neutron star, reducing its collapse and achieving a lower density. Consequently, the neutron star will rotate more slowly, and the generated magnetic field will be weaker. The rotation speed of the iron core could significantly influence the outcome of the collapse. For example, very slowly rotating iron cores might not trigger an explosion, as suggested by many advanced computer simulations. A slightly faster rotation could result in a more rapidly rotating neutron star with stronger magnetic fields, potentially leading to successful jet-induced supernovae. However, if the iron core rotates even faster, the resulting neutron star might rotate more slowly and generate weaker magnetic fields, possibly resulting in total collapse to form a black hole. While this is just a hypothesis, it demonstrates how considering rotation and magnetic fields can alter our understanding of the core collapse problem. What factors contribute to one star having a slower rotating iron core while another has a faster one? This is a challenging question currently under active research. As stars evolve from the main sequence to the iron core phase, there is a tendency for angular momentum to move outward from the faster inner core to the slower outer envelope, slowing down the spin of the iron core. The rate of this spin-down process may also depend on the magnetic field within the star, another area of ongoing research. Additionally, whether the star has a binary companion can influence the outcome. Two stars orbiting each other can transfer some of their orbital energy and angular momentum to each other's cores, potentially resulting in faster spinning cores. Alternatively, if the stars form a common envelope, they might merge to create one rapidly rotating core, which could lead to the formation of an iron core under certain conditions. Whether a supernova is successful and whether a star yields a neutron star or a black hole may thus depend on whether the star was part of a multiple star system at birth. As we conclude this thrilling segment about stars, get ready for even more captivating content about these celestial wonders in the latter part of the video. Stay tuned for more excitement, and make sure to hit that subscribe button.